Okay, well, good evening, everybody. Thank you for joining us this evening and your interest in the London and South East branch evening lecture series. Hopefully you know where to find information about our upcoming events. If not, it's events.iop.org. I'm Mark Telling. I'm the current Vice President for the membership of the Institute of Physics, but I'm also a member of the London and South East branch, and I'm responsible for this particular event. So tonight's speaker, I would like to introduce is Simone Sturniolo. And Simone has a PhD in physics acquired in Pavia, and where he studied the dynamics of polymers with nuclear magnetic resonance experiments. After that, he started working as a computational scientist with STFC, where he still is today, working from remote, of course. And during the course of the last year, he's provided software to support the UK's NMR crystallography community, as well as looking at the muon spin spectroscopy technique as well. So without further ado, let me introduce tonight's speaker, Simone Sturniolo.
Okay, thank you. Thank you everyone for coming to this virtual talk. As Marcus has told you, I'm a computational scientist, which means that I tend to work a bit at the edge between theory and experiment. Experimental physics usually deals mostly with actually fiddling with things, extracting data from it and trying to make sense of that, while theoretical physics mostly is about making use of maths and trying to infer the laws that govern nature from the results of the experiments. Now, how do simulations fit into that? I'm going to talk tonight about specifically how do computer simulations today fit into the issue of material science and chemistry, and so studying the structure of matter at the atomic level, or as I put it in the title of this talk, how to see atoms with a computer. So as a background to start us with, the very concept of atoms is very, very old. The word was actually coined by the philosopher Democritus almost 2,500 years ago, and already then the reason for developing this concept, however, was an attempt to explain the way that matter is. The idea behind the existence of atoms, of course, was that it made more sense that matter would become impossible to divide at one point, rather than being infinitely divisible every time, until you could always get a smaller bit. And but the logic behind what Democritus thought atoms were was also an attempt to explain the properties of matter that we observe, so the macroscopic properties, in terms of the atomic qualities, the properties of these tiny bits of matter that they are made of. And so, for example, Democritus would argue that the atoms of oil would be spheres, and hence, while oil ends up being slippery because it's made of all of these spheres that slide on top of each other. Or that, for example, the atoms of salt would be pointy, which is why they taste as they do, because they sort of sting your tongue as they touch it. Now, that is, of course, a view that may feel very primitive to us at this point, but you can already see the logic behind it that is still actually relevant to this day. And in a way, reality is actually even more astounding than what Democritus thought, because Democritus would probably think about atoms in terms of different types of atoms for a lot of different substances. Now, in reality, the situation is a bit different. Now, here I'm making a comparison. Consider Lego bricks, the famous construction toys. Every set in commerce of Lego bricks, of Lego models, comprises is born out of a variety of approximately 8,000 different types of pieces that have been made during the years. On the other hand, everything that we see in this universe, every star, planet, non-living and living thing, and every human being, as well as every Lego brick, is effectively made out of some combination of just 90 different types of atoms, 90 natural elements. There's a few more, but they're pretty much not existent in nature, so that's about all that you need. And that's a very small number of bricks out of which to build this much complexity. So how does that come about? And the answer is that all the complexity really comes about from structure, not from just the types of atoms themselves, but from how the atoms are organized. So here I've got a very quick overview of different sorts of structures that we can observe. At a very basic level, you can have substances that are made just of individual atoms. In fluid form, so liquids or gases, or in glass form, these atoms are just going to be sort of moving individually and kind of disordered. In other substances, you may have molecules, which are small groups of atoms with some structure, but fundamentally independent, with a finite number of atoms, like water, which is one atom of oxygen and two of hydrogen, and that still move sort of freely. But when you go to solid matter, then very often you have crystals, you have patterns, you have regular patterns, symmetric orderings of these atoms or molecules that organize themselves in this, very specific ways. And from this symmetry and disorder are born all of the properties that then we actually observe of the solid matter. And when we think about crystals, crystal is a word that we use also in common language in English. It's not just a technical term. But when we think about crystals, usually we think about something like this, like a quartz or something like an ice crystal, so a snowflake. These are certainly crystals, but in reality, from these more technical viewpoint, this is also made of crystals, as well as these are actually made of crystals. The difference here is that in the case of the quartz and the snowflake, the order of the crystal that is present at the atomic level carries all the way over to the macroscopic level. So an ordering in the water molecules that make up the ice, which is hexagonal, ends up producing an hexagonal snowflake. So this is, it's a very sort of emergent kind of property that carries all the way up to the scale where we can actually observe with our microscopes or naked eye. Well, when it comes to an iron nail, for example, there is order at the atomic level, but the actual that order ends at a scale that is still much smaller than what we can see with a naked eye. It's like sort of the micron kind of scale. And the same happens with a lot of organic compounds, like the ones that go into pharmaceuticals. So for example, here, if we could see each of these things at the atomic level, zooming in a lot closer, then this is more or less what we would see. Here we have 3D models of each of these substances. So for quartz, we have silicon dioxide. For the snowflake, we have hexagonal ice. For the nail, we have the form of iron, which is common at room temperature. Now, the nail is actually steel, so there's going to be some carbon in there, but most of it is going to be iron. And on the bottom right, we have paracetamol, which is a famous, anti-fever medication. And that's the molecule of paracetamol. And these molecules are also organized in a sort of a regular way. And it's interesting here to consider really how much changes at this level can affect the properties of matter at the macroscopic level. So one classic example is carbon. Elemental carbon exists in solid state in two forms that are common as minerals, that are found as minerals in nature. One of them is diamond. A diamond is made out of carbon. The carbon atoms are organized in this sort of pyramidal structure. And a diamond is hard, it's transparent, shiny, and kind of an insulator thermally or electrically. But then if the same carbon atoms are arranged in hexagonal sheets overlapping one with each other, then you get graphite, which is completely different. It's soft, it's black, and it's electrically conductive. However, and an interesting thing is also that if we take the same structure as diamond and we replace each carbon atom with the atom of the element that lies right below in the periodic table, which is silicon, and that, ought to have very similar chemical properties because that's how the periodic table works, then what you get is crystalline silicon, which is yet different. It's shiny, but it's dark, and it's a semiconductor, so neither insulator or conductive. It's what we use as a starting point to make electronics. So really, we can see here how unpredictable, can the changes be, how non-trivial can be the changes when you make even some small difference in the structure, the atomic structure. This thing snowballs into some completely different properties once you look at it at our scale, at a microscopic level. So how do we actually investigate these structures? How do we discover them? One common technique, just probably been the first one that we've used to explore this problem, is diffraction. By diffraction really is by diffraction I mean really a number of techniques, because the principle is the same for all of them, but they can use different radiation. So all of diffraction requires that we send some sort of highly energetic wave into the sample. And the main difference here is we can use X-rays, which are an electromagnetic wave, and they're quite common. But quantum mechanics tells us that some particles can also act as waves in some situations. And so, for example, you can also do a diffraction with neutrons. Either way, the principles are very simple. So here, and they're the same. Here we have 4 atoms in a row to represent sort of an array, a crystalline array of atoms. Imagine that this is actually going infinitely in every direction in a regular pattern. What happens is that if you send an incident beam of some wave at an angle to these atoms, then the wave is going to hit the atom and is going to bounce back, be diffracted as exactly. And this atom then is going to sort of send back a similar wave in this sort of circular ripples around it. And then each other atom is going to do the same. But because they are spaced, they're going to be hit by the incident wave at different times, and there's going to be a delay into how each of them emits back this wave. And this delay is going to be proportional to the incidence angle as well to the distance between the various atoms, so with their ordering in space. And basically it turns out that if you take a crystal and if you send beams from different directions, so you rotate it and keep sending the beam from different angles, and then you acquire the data on all the beams that are diffracted from it in this way, so all the radiation that comes out of it in different directions, then you can, with some math, reconstruct basically what the actual structure of the atoms inside is. And this is a very famous technique. It's, for example, how the double helix structure of DNA was discovered in 1952. The picture here is not the original one, but it should have looked quite similar because it's the same thing. It's an X-ray diffraction of the double helix of DNA. Now, what are the limits of diffraction, however? Well, there are 2 main things that really tend to be a practical limit to the power of this technique. The first one is crystal size. Now, the principle that I described earlier works best if you have an ideal case of an infinite sort of crystal. If you don't have an infinite crystal or a very large one, which is effectively infinite for all practical purposes compared to the size of the atoms, then you start having problems, because in that case, the beam that comes out is not quite as focused or precise, collimated, so to speak, as you would have with a very good large crystal. And that means that the measurements, the quality of the data that you get out is similarly blurred, and you lose precision on it. And sadly, sometimes you're not able to have a large crystal of something, maybe because it's simply too hard to actually grow one such big crystal. So there are compounds, there are materials where it's impossible to actually get very clean and very high quality diffraction data. And there is another problem, which is the mass of the atoms that are being probed. Now, the radiation that we're sending in the sample, of course, is used as a sort of a probe, as a way to test it and examine it. And if the atoms that the radiation is hitting are very massive, that's fine. The radiation is going to hit them and bounce back and not do much, usually, even if it's pretty energetic, because it's still like taking a pea shooter and shooting at a truck. The bullets are just going to bounce off without doing much damage. But if the atoms are light, and this especially involves hydrogen, which is the lightest of the atoms, and that is very common in organic molecules like the pharmaceuticals, which I mentioned earlier, then that becomes a problem, because the recoil of being hit by this radiation can actually send the atom moving around. And because we're trying to pinpoint down its position, of course, it's not a good thing if it moves, just like you can take a good picture of someone who's running and dancing. It's going to come out blurred. And so basically that's the same situation. When you try to identify the position of very light atoms with diffraction techniques, you tend to have very low quality data because of this effect. So there are compensating, there are of course a lot of other experimental techniques. I'm going to focus on another one, in part because it's also the one where I work with the most, and because it's sort of complementary to diffraction in this aspect. So I'm going to talk about magnetic resonance. Magnetic resonance is another technique that has been used to explore the structure of matter, but that has very different property and principles. The way that it works is it's based on the fact that some atoms, some atomic nuclei, possess a magnetic moment, which means that they act like small magnets. And if you apply a large magnetic field to a chunk of matter, these moments will align themselves with that field, much like the needle of a compass will align itself with the field of the Earth. However, this is just sort of an ideal situation. What happens in reality is that inside a piece of matter, each atom is not just going to experience the field applied from the outside with whatever, massive electromagnet or otherwise, other system we're using, but it's also going to experience other magnetic fields produced by the other atoms, which, remember, they also are sort of like magnets, and by electrons, which are in turn able to produce magnetic fields. And so the real magnetic field that the atom aligns itself to and experiences is going to be a bit modified by all of these additional contributions. And if we look at those contributions, if we can measure those contributions, then we can make a guess on what the atoms around the one that we're looking at, are doing, what's happening, and therefore about the structure, even if it's not entirely direct. And the way that this works in practice, without going too much into the technical details, because it's very, it takes quantum mechanics to really explain what's going on. But you can imagine all of these atoms like a lot of tuning forks, which are supposed to ring at a certain note, like usually for a tuning fork, it's the note A. But in practice, are all a bit of pitch because, you know, they may be being pinched, or there may be a crack, something that makes them go a bit off the actual note. And so someone plays the note, and the tuning forks resonate, and they re-emit back the note. But if you have good ear, you can listen to them and notice that some of them are higher or lower in pitch, you know, slightly higher or lower in pitch than they should be. And then, you know, deduce that maybe that one is having that issue or something else. Except, and really the mechanism is pretty much similar, except that instead of sound waves, it's actually radio waves that do this. But it's a very similar concept in terms of the actual mathematics involved. And this method was, for example, famously known to deduce the structure of the molecule of ethanol, you know, common alcohol. And the way that it worked is that you looked at the resonances, at the magnetic resonances of the hydrogen atoms, and because the molecule is structured like CH3, CH2, OH, each of these groups creates a different environment for the hydrogen atoms, which makes for different pitches, so to speak, so different magnetic fields. And you would see that there were, you know, these 3 different signals in a ratio of 3 to 2 to 1, because that's 3 hydrogen atoms that see one pitch, that's 2 hydrogen atoms that have another pitch, and that's 1 hydrogen atom that has a different pitch yet, which is the one given by being near an oxygen. And so through this analysis, it was possible to deduce, okay, then maybe the structure, the molecule has to be arranged this way. This is how it has to work. So this is a different, you know, a different approach to structure. Actually, quite less direct than what you do with diffractometry, but still, that's been very powerful throughout the years in studying these problems, these kind of structures. So really, what you have is that all of these approaches never give you a direct look at the structure as is, but rather they give you hints. And, you know, it's like having a password where you have some of the letters and you have to fill in the blanks to find as a word that makes sense and that respects those letters. And really what simulation brings to this, you know, what computers bring to this, is that we are now in a position where once we have these few hints, we can really consider solving this problem like one would brute force the problem of finding a password, namely just try every possible combination, you know, every possible arrangement of letters that makes sense and see which one actually ends up being the most logical, the most sensible. So how do simulations specifically feature into this? Right. Let's go back again to the principle in general of emergent properties. So suppose that we have one atomic structure of some kind of solid, you know, that we know that there's, well, we don't know the structure, we just know which chemicals are in, you know, which elements are in it. And once there is the structure, of course, a crystal of this compound is going to have some properties which are determined entirely by the laws of physics. So this part is just a natural consequence of the way that nature works. Then we can perform experiments on this piece of matter in order to extract more specific data on what its properties are, and we can do stuff like, yeah, the diffraction, so how does it diffract X-rays, or what is its magnetic resonance signal, from which we can start making a prediction or a guess about what the structure could be, possibly. But as I said before with the password example, that prediction is likely going to be incomplete, or at the very least is not going to be certain. So what can we do? Well, we can use simulations to complete the loop, because we can use simulations to apply what we know of the laws of physics to go from our guess for the structure to what would an hypothetical macroscopic chunk, you know, big chunk of this matter actually be like. And then we can still use simulation to say, okay, and once we have this hypothetical chunk of matter, what would it look like if we did this experiment on it? And completing this loop means that then we have simulated experimental results that we can compare with an actual experimental results. And if nothing has gone wrong in this process, then we expect them to be reasonably similar. And if they're not reasonably similar, and if we trust our simulations, then it means that our guess was wrong and we have to adjust our guess, and we can then keep going on in this loop and making small adjustments until we get to the point where we finally manage to have something that's consistent and that works out. So what do the simulations actually consist in? Well, now we have to look at how the properties of matter emerge in the first place. And the reality is that when you have any sort of arrangement of atoms, the atomic nuclei themselves contribute relatively little to the overall properties, at least not directly, because what atomic nuclei of different elements have, be them carbon or iron or gold or uranium, all of these just different in mass and in electric charge that they carry. What really ends up making a big difference is the electrons, because the electrons, which are the negative particles that orbit atoms, end up acting as a glue that keeps together the entire solid. And because of how quantum mechanics predicts that electrons behave, these particles are actually very wave-like because they are very light, and so they spread and interfere and form shapes that are not obvious. And the properties of the matter end up actually coming out mostly of how the electrons are arranged and behaved. And this includes things like the elasticity, the reaction to the thermal conductivity, electric conductivity, the magnetic properties. A lot of qualities are really the consequence of what electrons do. And the electrons fundamentally obey this equation most of the time. Well, this is sort of an approximation in principle, but it's a good one for the great majority of solids. And this is the Schrödinger equation. It's a differential equation. Without going into exactly what it means, the key concept is that this equation is something that we can solve with a computer, and that tells us how the electrons are arranged in space, which in turn is something from which we can derive pretty much every other quality of the matter that we're studying. So how does one go about solving such a problem with a computer? Well, again, there are two problems here. Well, main issues here that we have to confront. One of them is common to pretty much every representation of a real life thing into a digital form. And it's basically that computers work in discrete quantities. So for example, if you have to save an image into a computer, you have to split it in pixels. So you divide it in squares and you assign a color to each square, like here I've done for the Mona Lisa. And here we see the limit of that, because of course, if you take a very coarse division, in a very small number of squares, you end up not even realizing it's the Mona Lisa anymore. So you lose so much detail that you're not even looking at the same thing anymore. But in turn, when you increase the detail, you start seeing more the original thing, the thing that you're representing. So it's now a better approximation. It makes more sense. But at the same time, you have more squares, which means you have more numbers, which means you have a bigger file. So you're working with more data. And in the case of simulations of physical simulations, we're talking about amounts of data that are really taxing and really problematic to work with sometimes for even supercomputers. So of course, there's a balance here that we're talking about, where with the most complex systems, you have to strike, you have to find the golden middle between being too coarse and not actually representing well the system, and being too precise and taking way too much time for your calculations. And also we have to consider that was an image, you know, a two-dimensional example of a picture, but in reality, electrons are spread out in three-dimensional space, because that's how the world works. And so these are more voxels than pixels, really, that we're talking about, or sometimes even different shapes, but really the concept is always the same, that we need to divide space into pieces. Then the other problem is very peculiar instead to quantum mechanical simulations. And the problem is this. Suppose that you have a cube of space and you divide it with side L. So in this case, for example, I divided the side in 3. So the whole cube is divided in 3 by 3 by 3, 27 total voxels. Now the problem is that suppose that you have to describe how n electrons fit in this cube. How many numbers are you going to need? And what you're going to need, actually, you know, L times L times L, so L to the cube to the nth power. And this is a consequence of the way that quantum mechanics works. Quantum mechanics is a combinatoric theory, so you have to consider all possible combinations, you know, all possible arrangements of these n electrons in these 27 cubes, and that's how you get the number of combination in combinatorics. And that is a very large number, and that is a number that grows exponentially, literally, with the number of electrons, which makes it almost impossible to deal with any system that's larger than, you know, basically than very small, you know, any system that's in actual interest and not just an example. And so how do we deal with that? Well, one of the most common and most popular approximation is called density functional theory. And this is an approximation that allows us to rewrite the Schrödinger equation, sacrificing some precision for the sake of moving from that sort of, you know, size of the problem to this sort of size of the problem, where you actually have L times L times L times n amount of numbers that you need to describe the wave function of the electron, which is the solution of the equation. So again, we have these trade-offs where to not do something that's way too expensive, we do something that's a bit more imprecise, but, you know, and therefore we have to be careful and check that it actually works well. But if it does work well, we're finally in a situation where we can solve the problem practically, rather than having to face a problem that would take the age of the universe to run on a computer. So now I'm going to just show a more practical example of how this could work. Suppose that you have a new pharmaceutical, and you're tasked with studying it and trying to find out its crystal structure. So how would one go about doing something like that? Well, the first thing is you perform an experiment. Typically you perform a diffraction, an X-ray diffraction experiment, like I've described. Now let's work in the hypothesis that this actually works out well. So you get a good structure, except for the hydrogen atoms, because remember what I said, that in diffraction hydrogen atoms tends to get a bit rattled about, and so you don't have really good numbers for their position. So we just want to find the position of hydrogen atoms here. So how do we do that? We build a model, we add the hydrogen atoms in positions that we know are sort of sensible from our understanding of chemistry. And then we use simulations to adjust their position. So to move things in a way that they go to an equilibrium kind of situation where they don't move anymore. And then after doing that again, we use simulation, this time to predict what the NMR results would be. So to predict what the internal magnetic fields, you know, generated from all of these atoms are like. And then we can compare that to a real NMR experiment. And if we've done the work right, we're going to see two results that are very similar from this, which is going to tell us, you know, okay, we've found our structure, we can stop. Now, what if it's not this simple? What if we find out that the structure that we got from X-ray diffraction is not that good? So maybe we have only a partial structure, some information, but we don't have all of it. Or maybe we just found out, that there's some mistake. Then we have to use simulation, to push the role of simulation a step further. So what I represented here is what we call the energy landscape of a structure. In other words, supposing that you know that there are a certain number of molecules inside a crystal, each of their arrangement is going to come with a certain energy that represents how much they are comfortable with each other, so to speak. Are they fitting well, or are they clashing? If they're clashing, the energy is going to be high because they're repelling each other. If they're fitting well, then the energy is going to be low. And usually the structure that is stable, the one that you want to find, that is the actual way that molecules are arranged in the matter, is the one of the lowest energy, which is the sort of equilibrium configuration. So the way that you can look for this structure without knowing, in principle, anything about it, can be actually very simple. You can simply start from random points. This technique is called the ab initio random structure searching, which was developed originally by Professor Chris Picard. And the idea is simply to generate a lot of random structures using whatever criteria we already, whatever knowledge we already have to constrain them, which one they generate, and then use simulation to move all of these structures, to try to find if there are tensions and to relax the tensions in these structures so that they move towards a more low energy configuration. And in principle, of course, after a while, we should find that a lot of these end up being looking like our stable structure, lowest energy structure. Once we have that, then we can pass to the next step of predicting the results of the experiments like NMR and X-ray diffraction and comparing against the real life experiments. And then again, closing the loop, verifying if it works. If it doesn't, then we have to change something and so on. Now, an even more complex case, maybe what if not only we don't get a good structure, a single good structure, but we have signs, we have hints that there may be multiple structure existing. So this is a phenomenon called polymorphism, and it happens quite a lot, especially with organic molecules like pharmaceuticals, where there may be more than one structure, crystal structure that you can find at the same time. Now, in this case, the energy landscape, so to speak, would look more like this, with a lot of valleys, each of them representing one different structure that is viable. And in this case, we can use something like ERS that I described earlier, just with an additional step that I'm going to describe. So we start still with a lot of random structure points, random points on the energy landscape, basically. Then we relax the structures, so we try to move them towards the closest sort of equilibrium point. And once that's done, we use some analysis techniques like machine learning techniques to identify which groups of structures are similar to each other. And so, go and find these valleys in the form of similarity. We have a bunch of these structures that we tried, and they all end up having similar qualities, similar look. And this is done, it's similar to having an algorithm decide which pictures are of the same person, even if they are taken from different angles, for example. So that's why we go with clustering and techniques that are machine learning based. And then we can go over a representative of each candidate structure and do again the tests where we try to predict results like NMR or X-ray diffraction. And once that's done, deciding which one of these actually matches the experiments that we performed and therefore is likely to be the real structure that we are seeing the most of in when we synthesize the compound in a certain way. Now, what if the what are the applications in the future of this sort of technique? Well, pharmaceuticals, I mentioned them a lot because they are an important part of this. Now, when it comes to pharmaceuticals, the structure of the molecules is usually what decides whether they work, whatever they have to do inside the human body. But the crystal structure of the molecule, when you make it into a solid, is what defines a lot of qualities like the solubility, so how much it dissolves in water or in gastric acid or whatever after you eat it. So that's important for how quickly it gets absorbed. And then things like shelf life, how long does it take to decay, to lose its properties and expire. So there is a lot of interest in studying these things, even if it's not about just making necessarily the medicines that work. It's more about making sure that they don't spoil before you take them, or that they get absorbed properly and they don't go to waste. Another big field in which it's important to determine structural materials is energy. So everything that has to do, with hydrogen storage, fuel cell membranes, zeolites, batteries, battery materials, all of these, to optimize these things, we need to understand very well what's going on at the atomic level, all of their properties, all of the phenomena that are ongoing, because sometimes it's a matter of even tuning very small amounts of one additional element or another into a compound to change its properties. And then more in general, there's this idea that if you develop enough databases of simulation results of various sorts, you can do maybe automated materials research. So that would be the idea that you can actually start scavenging all of these data and putting it together, maybe training neural networks on it, and start seeing if you can generate new ideas for new materials that we can create with given properties that we want out of them, just as extrapolations from all of these knowledge. And I have to say, we actually have made a small step in this direction. So during the last year, I actually created and deployed to the web this database of NMR computational results that is sort of one step in this process, but this is of course a very long way. That we're sort of just starting now, because it's still not something that's common enough, and where there is enough work to really have the massive numbers of structures that we need for this sort of thing. So thanks for your attention. That is all. There are any questions?
Thank you, Simone. Thank you very much. Can you hear me? Are you there?
Yeah. I hear you.
Fine. Fascinating. Thank you so much. Yeah, we've got some questions coming in. Thank you to the audience for submitting them. So I'll start with, I think it's Nina Reddy, who wants to know, I was wondering, what determines whether an atom has a magnetic moment or not? Thank you. So some fundamental magnetism.
Okay, so this is actually this is more of a particle physics problem, really. But the thing goes like this: protons and neutrons all have magnetic moments. So, for example, a hydrogen atom, which is just a single proton, has definitely a magnetic moment, which is the magnetic moment of the proton. Now, when you have multiple protons or neutrons, which is basically in every other element, what happens to the magnetic moment depends on how these things interact, and these things interact between them, not just electromagnetically, but through the strong force, through gluons, which, I mean, those things are simulated too. That's called quantum lattice quantum chromodynamics. I don't do that, and I don't think that's that. I think that's actually not yet entirely well understood. So I don't know if we can predict these things from first principles. But for example, deuterium, which is a neutron and a proton has a magnetic moment of 1, because they're aligned, they sum together, 1/2 and 1/2 each, they become 1. But in other cases, they may be, there may be atoms where they're not aligned and they sort of cancel out each other. And what state the atom is actually in, that depends on these sort of complex interactions. Different isotopes of the same element can have different spins. For example, carbon-12, which is the most common isotope of carbon, does not have a magnetic moment. Carbon-13, which is a much less common isotope, does have a magnetic moment. You add one neutron and everything changes, and now a magnetic moment arises. So yes, this is more or less it. In practice, we just have tables. That's about it. We've measured these quantities for the entire periodic table of the elements, and we have tables of this data. I don't know if it can be predicted from first principles, and we certainly don't do that.
Thank you very much. Thank you, Nena. Thank you. I was just wondering myself, can you say something about the computing power that's needed for these simulations, these calculations? I mean, what can you do on a desktop these days compared to what you can do on a cluster?
So it varies a lot. It varies also based on the level of accuracy that you want. There are different levels of techniques. I can tell you, like, there's a technique called density functional type binding, which is very simplistic, so to speak. To give you an idea, I talked about describing the electrons as clouds that are spread across the entirety of space. That would be what we do in a proper density functional theory calculation. In a density functional type binding calculation, it's a bit more like the chemist's view, the one that uses orbitals, and that just describes the electrons that are orbiting this atom or that atom. So it works decently for molecules, and and maybe less well for things like metals, where the electrons are a lot more spread out. If you want to look into that, there's actually a program called DFTB Plus, which can be found, which does density functional type binding, which is open source, free to find, and you can run it on your desktop. You want to do something like a water molecule, a small, aspirin molecule, sugar, whatever, right? All of these things, you can really run them in a few seconds. Now, if you want to do that with a DFT program, depends on the program heavily, because even these, change a lot. The algorithms change a lot, and that changes a lot in terms of what you can get. But I would say you still can do something like that in a matter of minutes, 10 or 15 minutes. If you have a powerful desktop computer, like 8-core, 16 cores, you want to use them in parallel, I guess you could do some, some decent level calculations even on your desktop. I can say that for simple systems, even on a cluster, I would probably use 16 or 32 cores, not that much in terms of power, and they would be done in 1 hour or 2, if you're willing to leave your computer on, and do things overnight. For really large, really complex things, definitely you couldn't do, absolutely, almost not even in the most powerful computer in the world, something like a protein. Like, you could, the spike protein of SARS-CoV-2. That's not, you're not going to do DFT on that. Probably not the regular kind of DFT, at least. You can probably do some linear scaling DFT, like with one time. But I mean, most of these techniques that I described, they wouldn't work even on a very large supercomputer, because the size makes the cost go up exponentially, really dramatically. As a general rule, I would say something that has some 100 or 200 electrons is in the range of what's feasible. So 100 or 200 atoms will start getting expensive. 1,000 atoms, that's really expensive, and then it depends on what quantities exactly you want to compute.
Okay. Oh, no, thank you. Thank you. Nana, I've seen your second question. I'll get to that in a second, but Walter's been waiting. So Walter Andrews would like to know, how can an electron leap between atomic levels without passing through all the space between? Wow, quantum
Uh,
mechanics.
uh, well, I don't think that's necessary. I mean, I think there's a problem there in seeing them as there's no space between, basically. I mean, usually, actually, when an electron can leap between two orbitals, so to speak, so-called orbitals, the two orbitals actually do overlap. Um, you should see them, it's more like a Venn diagram of sorts. It's like, oh, there's electron in this region or electron in this region. And usually when the electron can jump, it's because they intersect. So you could see, like, well, they overlap a little, and actually how much they overlap is often a factor, is generally a factor into how likely it is for the electron to jump from one side to the other. So this is sort of the way that you can rationalize it, I guess. So really, when you get to a point of actually looking at the equation of quantum mechanics, the whole concept of just space and moving from one point to another is not really the best way of thinking about them. So you could say you're not thinking four-dimensional. You used to say Doc Brown in Back to the Future, right? And so you're not thinking quantum mechanically in a way. but I realize that that's not super intuitive. So I think this is sort of the most intuitive explanation that I can give of what's going on there.
All right, thank you. Okay, so we're just going to hop back to the first question from Nana again. She says, thank you for answering my question. So just to check, is spin the same thing as magnetic moment? Thank you.
Yes, in this concept, well, in this context, it was. When we're talking about nuclei, then yes, spin is angular moment. So it's something that's connected. That it's kind of like a rotation, even though again, quantum mechanics is not actually a rotation, but it's connected to rotational symmetry at the very least. Yeah, that let's leave it at that for now. But yes, spin for a charged particle turns into having a magnetic moment. Just like if you rotate, a charged sphere, even in classical electrodynamics, you get a magnetic moment. However, when we're talking about NMR, the magnetic fields that the atoms experience are also due to some sorts of magnetic moments that are not due to spin. So in regular electrodynamics, we get magnetic fields when you run a current into a coil. So even just a current that loops around is enough to create a magnetic field, right? And the same happens at the atomic level. When you apply a magnetic field, you get currents, you get electronic currents, you get electrons that sort of move in loops. And in doing that, they also generate magnetic fields that are not spin, that are not born out of spin, which is the intrinsic angular moment of a particle, but they are born out of, particles actually sort of moving in circles. Again, the quantum mechanical equivalent of moving in circles, which is not quite what we would think normally as moving in circles. There's more there, but in general, that's more or less the concept. So there's also these sort of currents that create magnetic fields.
Okay, thank you very much. So we're coming to the end of this session, 5 minutes. If we've got any final questions, please put them in the chat box. While I wait to see if anything comes in, I just want, what are the next challenges for you in your work? Where are you heading?
So, well, right now, I mean, there's actually one of the next things that I'm going to do is a web development project, because we're trying to improve some software that people use to visualize these results. So these results are not very intuitive to look at when they come out of the software. They just these long text files with a lot of numbers in them. And so we also created, I'm also creating and maintaining this program that allows people to visualize nice 3D structures of their atomic structures, and then have nice plots, shapes, arrows and things that actually plot the data on top of the structure so that it makes no sense and it's easy to interpret.
Yeah.
And then another thing that I'm working on is simulations of transitions. So this has to do more with something like chemical reactions, where you want to figure out, you know that this is the starting point, like 2 compounds, and this is the end point, 2 different compounds. How do you go from A to B? Which usually involves finding sort of a middle point that represents, that sort of, well, it's like finding the frames of a movie where you want to figure out how exactly you go from one point to the other, and we can do that with simulations too, or at least there are ways to try and do it. So that I'm developing these algorithms inside one of the major simulation packages.
Oh, thank you. I mean, I guess that this technique, any kind of simulation, while you need to visualize the result, it's never going to be a black box. You really have to understand what's going in, what's happening, and then what's coming out. So you're never going to get an app to simulate a molecule.
This is always a problem, right? Because most users, I mean, this is not just complete laymen. Even experimental scientists often have very limited knowledge of what's actually going on in the simulation. So really, when you develop software like this, it's usually important that it behaves as sensibly as possible, because you can't necessarily rely on the users being super experts that are going to be able to figure out what's going wrong, or whether some result is actually not unreliable. So I would say that while it would probably be too much to hope to have some sort of complete black box where molecule goes in, paper comes out. I think that for some limited cases, especially in organic chemistry, where the processes involved are relatively simple, you could have some hope of having that, like having to put very little critical thought, because in the end, a lot of these things are relatively well behaved and similar to each other. I mean, the structures are different, but the actual phenomena that are going on are very sort of predictable. That is definitely not the case, however, if you start thinking about some very complex materials like superconductors. Superconductors are terrible. They're extremely, you actually wouldn't, like a regular DFT simulation wouldn't even get to the superconductive, because the physics involved are so complicated, and they're completely waved away by all the approximation that we're doing. So there is a lot of difference depending on what it is that you're interested in.
Okay, thank you very much. Okay, everybody, it's 7 o'clock. First of all, can we thank, if you were here, can we all give Simone a huge round of applause? I'm sure you're doing it at home or wherever you're watching. Please check the events.iop.org for our future online webinar series between now and summer. I hope to see you again at a future online seminar. Thank you very much, Simone. Take care. Goodbye, everybody.
Bye.